So it is 8450 plus 51. Sorry, plus 50. This is 8500 plus 51. Totally, it is 8551. Can you see massively we have reduced the model parameters with CNN? We have massively reduced the model parameters. Each and every pixel, there is no need to allocate one weight. That is a fundamental idea, logic you should understand, isn't it? The logic is each and every pixel, I no need to allocate one weight. After all, these pixels are highly spatially correlated. That is the reason we are applying the weight over the image using a convolution operation. Same set of weights are being operated over the image. We keep shifting and we are applying. We keep shifting, we are applying and updating the values. So first of all, that there is a less redundancy in this approach. Number two, it's computationally it's faster. It is a too many model parameters to update, and moreover, it is not effective, and it is a highly inefficient algorithm because it has lots of redundant information here. Here we have a less redundant information. And moreover, we have less number of model parameters to update. Is that clear, the calculation? How do we get 39,301 and 8551? As if you are increasing the filter, maybe again, the parameters will increase. Suppose instead of one filter, when I change this to two filters, with two filters, what will happen?
Into 2.
No, it's not into 2. Okay, quickly let us calculate with two filters. How many model parameters with the two filters? What are the changes that happens? I just quickly tell you. You are going to use two masks, right? So two masks. So for one mask, you got 9 weights. For another mask, you have got another 9. Okay. So when you flatten, you got 169. This also you got 13 by 30. You have got another 169. This layer is same. Once again, you multiply by 50. Here also you multiply by 50. Plus 50. Plus 50. Plus 51. Plus 51. Yeah, correct. Into 2 only. So here I forgot to add this 9 here, isn't it? I didn't add. So in this, you should add 9. So the score is 8,560. So with the two filter, the model parameter is 8,560 into 2. 17,120. Am I right? 17,120 is the model parameters, number of model parameters. Okay, one final calculation. One more final calculation. If it is instead of grayscale, it is a color image. Color image with the two filters. One last calculation. Color image with the two filters. How many model parameters?
It will multiply by 3. Into 3 will get.
Can you work out the number, final number you tell me? In the meanwhile, I just work out the calculation. Let me cross check that number. Give me the final score. You can put it in the chat box. You tell your calculation. Let me share my calculation. Let us cross check both, and you correct me if I'm doing any mistake. So for for one filter alone, we get 25,419. So for with two filters, you double this number. 50,838. So total 50,838. Please cross check and let me know. Is it right? Because 169 will go to 3 channels. So that is why 169 multiplied by 3. And then that has to be multiplied by 50 neurons in the hidden layer. So that will give 25,350 plus 50 plus 51 plus
Sir,
8.
how
So
is
how
that
did that 18
18?
come? Okay. Yeah.
Huh? 9 plus 9,
Huh.
2 filters, right? 2 filters. Oh, sorry. 2 filters, I'm doing separate calculation. So it is 9. So 169 into 50 into 3, 25,350 plus 50 plus 51 plus 9, 25,460. Actually, this is 25,460. 25,460 into 2. 5920. Okay, 5920 is answer. So the total is 5920. This is this into 2. Is it right? If it's 9 plus 9, if you're adding, keep it at one place. I have kept at both the place. That's a mistake. So 9 plus 9, add and keep it at one place as 18. Okay, now let us, everybody clear about this? Shall we move on?
Sir, when we say here 2 filters, basically it's like a filter, then a max pool, then a filter, then a max pool. Is it like that, or is it like 2 filters and then a max pool?
Only one CNN layer with the 2 filters. I didn't see, the flow is very important. No, I didn't draw like this. If I have drawn like CNN max pool, CNN max pool, then the calculation will be different. Okay, but I didn't specify like that. In the CNN itself, I specified 2 filters.
Okay. And what will be in the other case? Like
CNN max pool, CNN max pool.
yes.
Okay, that also will work out one last case. Suppose instead of this architecture, okay, this architecture is 5920, right? Let us store this value. 5920, 920. Suppose I'll go with CNN max pool, CNN max pool. This kind of architecture when I go with. So 9 weights. So here you got 13 by 13. Okay. Here also, if I'm applying the same size filter, assume if I'm applying same size filter, what will be the output? 11 by 11, am I right? 11 by 11. This output will be, it will discard the fraction. If it gets 5.5, we cannot have 5.5. So 5 row, 5 columns in the output. So once you flatten this, you get 25, right? 25 into 50 plus 51.
Got it. Yes.
This way. So what is the total number of weights? It is 25 into 50 plus 51. And finally plus 9. Comparatively, you will get less number of parameters here. So 25 into 50 plus 51, 1301 plus 9, 1310.
Into 3 also for like it's a color image.
Yeah, if it is a color image, into 3. Okay, 3930. So massive reduction. So if you wanted to reduce the model parameters, you can go this kind of logic, CNN followed by max pool. If you wanted to represent reduced number of feature space. So your feature space is getting reduced. Here you are representing your image with 169 features. Here you are representing with only with 25 features. So according to the complexity, if you feel that image complexity is very high, you can represent with more feature. If you feel that, okay, the complexity of the image is not that high, if it is the image is simple, maybe you can go with this kind of architecture, could be better. At the end of the day, experimentation is the only answer for whenever you construct a deep learning architecture. There is no free hunch. You explore all the possibilities and finally arrive which architecture is giving you the better result. See, except your tabular data set, other than tabular data set, when you work on image, other forms of data sets like image, time series, and text. On the other side, I just keep the tabular data sets. In tabular data sets, you do EDA. Can you tell me what is the overall objective of doing this EDA? Overall purpose of this EDA? The overall purpose of the EDA is going to boils down to at one point. What is that? EDA is going to indirectly help you what?
Feature engineering.
Very good. To arrive the final set of feature for your model, isn't it? EDA is going to give you an idea about how each and every variable associated with your target variable works. And you are trying to explore whether it is a linearly dependent or non-linearly dependent. If it is a linearly associated, you are checking, okay, whether all for the linear model, whether all statistical assumptions are satisfying or not. If it is not satisfying, okay, let me go to non-linear model. So indirectly, you are working on what is the final set of features I'm going to use for my model. Similarly, these type of data set that you are not typically doing a tabular data set kind of EDA, but indirectly you are working on a different aspects of exploring. That means you are bringing this data set suitable for the model. For the images in the form of a CNN layer, you are finally bringing a particular suitable form of, after flattening, this is going to represent the final feature for your data. Similarly, time series data set also you perform one-dimensional convolution and you are representing a proper representation of this data to the model. Because as a raw data, I cannot take this to my model in a raw format. My model will underfit. That is why you are bringing some kind of a feature engineering in the form of a CNN. You are bringing to the suitable form to your model. Similarly, for the time series data set also, there are two possibilities. One is manually you can apply the formula and extract features. If you don't have a domain knowledge on the image processing, you can go with the CNN based. Similarly, for the time series also, if you know digital signal processing domain knowledge, you can apply, still you can apply some features you can extract in the time domain, some feature you can convert this to Fourier transform, extract in the frequency domain. Still you can come up with your own features, bring it to the tabular form, and still you can apply. No need to use a one-dimensional convolution also. So this one-dimensional convolution CNN based is another alternative. Another alternative, of course, it's a very successful alternative. Almost 75% of the applications, people are adapting this technique. So seven projects out of every 10 projects, they are adapting this technique. Maybe the remaining 2 to 3 projects, they may be working with the conventional approaches also. Same thing, it's applicable for the text data also. Whenever we work on the text data, in general, natural language processing, which includes the speech signal also. So already in the time series, we have included speech also. It's a part of a time series. So other than speech, we work on the text data. In text data also, we are going to know about what are all the different strategies to represent the text in a meaningful form to the model. So I will tell early days how people have represented a text to numbers, and in a modern day, where they are standing in. So most of the recent models, deep learning architecture, what is the recent development in the text representation? From the very crude approach to the very modern approach, what is the thing they are following? So in this session, today's session, I'm going to focus on the different pre-processing methods used for the text. Of course, towards the end of the session, I will build one model and I'll show you. And the latest, whatever the latest pre-processing method is being adapted, that approach I'll be introducing tomorrow, followed by again a deep learning strategy. So today we will be learning couple of approach. Okay, couple of approach. Say approach number 1 and approach number 2. What are the limitations in this approach? Okay, with this approach, what kind of design is possible? What kind of DL design is possible? That we'll be end up in doing it. Okay. Tomorrow I'll introduce the third approach. Because of this approach, okay, what are the capabilities I can enhance in my DL design architecture? That also. So primarily today and tomorrow session, the focus is on the end application is what? My end application is, it's a classification model again. At the end of the day, I need to classify the text. So both one example we are going to see multi-class, another example we are going to see the binary class. So in tomorrow's session, I'll be building sentimental analysis. So for sentimental analysis, I take binary class, positive sentiment and negative sentiment. Okay, tomorrow's session is on the sentiment analysis. That is also a part of classification. Today example, my pre-processing approach is slightly different. And I'll be end up in once again classification model, but my modeling approach is slightly different approach. This is a multi-class. So in modeling approach, why these two approaches are slightly different in modeling? In what way they are slightly different? Towards the end of the session, you will come to know that. So first, let us focus on some basics on data preparation. Again, I'll tell you what are all the packages, also how it evolved over a period of time. Earlier days, people have predominantly used NLTK packages. This is a popular package to process the text. dataset, NLTK, Natural Language Toolkit. So in recent times, people are using Space. So this is more Spacey, SPACY. Spacey is the most advanced and recent toolkit to process the text data. So initial few exercises, of course, I'll be using and demonstrating NLTK. We are not completely wiped out NLTK. Okay, still some capabilities are NLTK is having in terms of rich library sets. NLTK is still it is having a very rich databases. Okay, always in case if you don't have your own databases, NLTK is having a varieties of databases. Whether you wanted to build an application for the linguistic application or web-based, suppose you wanted to, for example, you wanted to scrap all these social media data. Again, NLTK is having a rich resources of data, and particularly multiple language pools are available, including Indian languages and foreign languages. NLTK having a rich data sets available. If you wanted to particularly build some experimentation on non-proprietary data sets, non-proprietary, you know what is the meaning of non-proprietary, which is not binded to any client. So NLTK is having a rich set of data sets. I mean to say that they are copyright-free data set. The first and foremost process in the text thing is we have to extract the words. So we used to call it as the tokens. We call it as a tokenization process. So based on the white spaces, it is going to extract and filter all the tokens. And once we got the tokens, how we are going to represent the tokens, one approach to another approach is going to vary. And again, it is evolved over a period of time. Almost I could say that period of this evolution has happened some 6 to 8 years evolution. It not happened in overnight. So one approaches, people understood the drawback, and another set of researchers has contributed some improvement. Again, people understand there is a lack of certain issues, and again they overcome it, and they keep on improving the representation. And in modern day, the most advanced representation is a word to vector representation, word embeddings. That is the most recent representations. So before that, let me share one sample text file. All of you first load that txt file, and we'll work out some basic pre-processing step. We'll just get some first-hand exposure in some basic pre-processing with the text. Then we'll start working with some really some big file. Okay, first let me give you one small sample file. This is not really a big file. Okay, first to understand the process, let us understand the process with the small toy data. Then I'll give you some real big file. We are going to apply the same process with that big file, and also we are going to appreciate different methodologies, the pre-processing methodologies, how we are going to prepare the text in a suitable format for the models. So the name of the text file I have created for the initial pre-processing experimentation as sample.txt file. Let me share the link of that. Please download and upload in your current working directory. It's just some 5 to 6 line of a text. So download the sample.txt file. So I'm loading the file here. So I'm naming this as a session 7, exercise 7. We have a 2 component in exercise 7. Okay, so I splitted my file as 7A and 7B. So 7A is predominantly on the different pre-processing, 2 different pre-processing techniques we are going to see here. Followed by 7B exercise, we are going to implement the model. Okay, once we prepare the data set, we are going to implement the model. A model on some real data set. Okay, that is a real data set, which is a copyright-free data set. So there is no intellectual property binding on this data set. You can open the txt file on the basic Python IO operation, file IO operation. There is no nothing special package required to read this txt file. So you can use simple open operation to read the sample.txt. Okay, in read write mode, in read and editing mode. That is why RT. So first you open the file using this command. So my file is loaded. Okay. So don't just because spacey is what most of the people are using in modern day doesn't mean that we have to completely omit NLTK. You should got some exposure with the NLTK also. You should got some exposure in the NLTK. Particularly the young generation, what I have seen, whatever the latest, that alone they straight away they are learning that. That is, see, without approaching the earlier approaches or some classical approaches, directly if you jump into the modern approach, you will feel something like, okay, why it is like this, and you may not appreciate what was the bottleneck in the earlier approach, how this has been evolved. Really, you may not appreciate the beauty of the advanced model. Unless otherwise you go through certain difficulty, okay, this is a challenge, and that is how the people have came up with this kind of a solution. That evolution process you may miss. Not only on the package side, I'm telling, in terms of that is the reason even in the neural network architecture, we started from the scratch. McLaughlin's model, what is the drawback? Then perceptron model, again, what is the drawback? Then delta learning rule. That evolution will give you an idea, clear picture. The same thing on the package side also. Many youngsters I have seen in the interview, when I interview, they will say that never we worked on the NLTK package, because that is the base. Without going through with the NLTK package, okay, there is nothing harm in learning phasey, but go through some basics of the NLTK package also. This is something like you are jumping into the Hadoop without having the basics of SQL, something like that. Because SQL is the base for any big data architecture, isn't it? At least you need the table operations, the basic table operations. Then, of course, you can easily migrate to a Spark or Hadoop file system, and whatever the system, you can easily migrate it. The base is like a SQL. Similarly, for NLP, your NLTK package is the base. Just go through some basics of NLTK utilization, and then you can migrate to any advanced package. So along with NLTK, I need to download this PUNKT package also. So using this NLTK, we are going to do some pre-processing on the text. So I have loaded this file in the variable text. Okay, text. Even you can type text and display this. So you can see the complete paragraph, the whole text you can see here. It is one small paragraph about computer vision. Computer vision is not just a way to convert pictures to pictures. It can't make sense of pictures like. So maybe how many sentences? 1, 2, 3, around 5, 6 sentences, I guess. Yeah, 6 sentences are there. Okay. So now using NLTK package, I'm going to tokenize this text based on. So this NLTK tokenized package is going to tokenize the text based on the white spaces. This NLTK package is having some sentence tokenization also. Instead of word underscore tokenize, if you call sentence underscore tokenize, it will do the sentence tokenization. Some applications, they may use a sentence tokenization, mostly like linguistic applications. see some lexicography understanding and all. The people are using NLP to understand, okay, the quality of the literatures, the vocabulary richness, okay, and the grammar. All those things is what the linguistic analysis. So for linguistic analysis, certain cases they wanted to comprehend sentence-wise tokenization might be needed, but predominantly, other than the linguistic applications, predominantly like most of the applications we are using this text pre-processing. Can you name few applications whichever is coming in your mind? Can you name on day-to-day process wherever, which are all the areas you have seen text-based AI models you have seen? Any few applications, quickly tell me.
Next word prediction in our messaging apps.
Okay, next word prediction. Then
And then voice commands, speech to text, it converts like any Siri or Alexa.
okay, speech to text. Text to text, have you seen anywhere?
Yeah, those apps, I guess, from one language to another. Build that.
Okay, this is text to text is one language to another. Where else you have seen this text to text? Bot, yeah, very good. Whenever you open any website, it is giving auto reply, right, to your text. There also you have seen text to text. Then does Amazon, Flipkart portals, they are using text for anything? Just for your quick understanding, I'm telling, but there are so many e-commerce portal, not only e-commerce portal, many portals they are using this text preparation for certain application. Okay, that is one is chatbot, right? This is about chatbot. Chatbot we have seen.
Reviews, in reviews also, it is summarization of reviews, text summarization.
Okay, text summarization. Okay, text summarization. Have you heard about recommendation systems? Recommendation systems.
Yes.
Basically, we are getting recommendations based on the text based. Your content, what is the content is what your each and every product, whatever product or services you see online, it is being described in the form of a text. Majority of the applications, whatever the application I have specified here, majority of the applications, okay, except some chat box, sentence to sentence, language to languages, remaining majority of the application, at least I can say some 60 to 70% of the applications, we need a word tokenization. Some special applications, special cases, we may require a sentence tokenization. Okay, now I have converted the whole paragraph into tokens. Okay, now let us check the length of tokens. Can you verify how many tokens we have got for this paragraph? Length of tokens, 126 words. Okay, totally the whole paragraph, this whole paragraph is having 126 tokens. Let me display these tokens for you and see tokens. You can see each and every word is a token.
Sir, it's displaying comma as a separate token. Can you scroll up where you are displaying the text? Up. Yeah. So if we see the first line, convert pictures to pixels, comma. So pixels and comma shouldn't be as one token because it separates on white space. It's giving us two tokens, pixel and
yeah, comma also it is separating, comma also it is giving us a separate token that we can filter it. All the unwanted things we can filter it. So we are not going to use it as this. See, the first thing I'm going to do once I convert it to tokens, you can see all my tokens should have some uniformity. Okay, what do you mean by uniformity? Say, for example, each and every token should start with lowercase. See, for example, this capital letter W. Okay, so otherwise it will treat small letter WE as a separate token, capital letter WE as a separate token. So one standardization is, once you got the token, I should keep all my words starting with the lowercase. Okay, so that is the first data preparation I'm going to do. Words lower. So we are going to standardize. I'm just doing a simple list comprehension. So I'm not using any package. I'm not seeking any help of any package. So simple, using a simple list comprehension, I'm doing w.lower string operation. Basically, it's a string operation. W.lower for W in tokens. So I got this words lower. So once you got this words lower, now you display this words lower and see. Earlier you have seen some tokens starts with capital letter. Okay, earlier. So before you convert to lower cases. See, for example, this computer C as a reference, and the V also, we have seen one V in capital letter. You take some 1 or 2 words as a reference. After that, you can check. Can you see this computer? It starts with lowercase, and that V also, so lower cases. So all the tokens starting with the lowercase. So your length remains same as 126. Okay, your length remains same as 126. If you wanted to do sentence tokenization, you have a functionality called sentence tokenization. Still, we are going to do some few more processing. Okay, we are going to filter out all English stop words and all. We'll do that. So before that, let me demonstrate sentence tokenization. So when I do sentence tokenization for the text, we have seen totally we have got 6 sentences, right? You just print the first sentence. So this is my first sentence. So based on the full stop, it is going to tokenize. So this is my first sentence. And second sentence is this. The second sentence. So totally we have got 6 sentences. So according to the application, you can tokenize whether word tokenization or sentence tokenization. You can do that. Okay, once you have converted all the tokens to lower cases, now I'm going to use, if it is any numbers, maybe some years, some size, something, because every text description has some numeric information also will be coming as part of the sentences. If you wanted to skip, eliminate those things, I am going to filter, remove remaining tokens that are not alphabetic. Okay, so again for that I am achieving that using a simple list comprehension without the support of any special package for this. So this time my input is word lawyers. Okay, words lawyer. Already we have converted to lower cases, and that is being stored in words lawyer. So word for word in words lawyer, if word is alphabetic. Non-alphabetic stuff has to be removed. If it is any numbers, numeric representation is there in the tokens, that has to be removed, which is not an alphabetic. So words updated. Now if you check the length of the words updated, earlier it was showing 126. Now it is 112. So the basic pre-processing is what we have to make all the tokens starting from the lowercase, then numerical component has to be removed, then English stop words has to be removed. These are the basic things. Of course, some advanced steps are there, but for those advanced processing, we'll be making use of the built-in packages. Not necessary to use the course, you can, there are some, even without using this advanced packages, you can do it, but you have to stretch that coding. It will, you have to write your own coding strategy for that using basic string operations. That will be a bit lengthy approaches. Whichever is possible with one-liner approaches, always you can do it like a list comprehension like this. If it is a bit complicated and too many steps are involved, always you can seek NLTK package or Spacey package for those things. Now I need to do one calculation called each word is appearing how many times? Is there a repetition? How many times it is appearing? So for that, I'm going to use the function called frequency distribution. So basically, it is going to do the word count. How many times that word, that token is being repeated in the text. So I make use of this frequency of the words updated. Okay, this is the updated words, right? I'm using that updated words for the frequency distribution. And also I'm displaying the top 20 f dot most common, highest occurrence to the least occurrence. Okay, or you can display the top 10, which are the words appearing too frequent. Mostly you can see the English top words are appearing in too frequent, right? And we of the, of course, for content based applications, of course, we have to filter all those things. Okay, I will show you, that is the next step. We are going to filter out these things. Of course, this is not going to carry any content about that product or services. Okay, but however, we still, since we have not filtered out these guys, it is being appeared. So at this stage itself, your comma, full stop and all is being removed, isn't it? Naturally, your comma and full stop also being removed at this stage.
Excuse me, sir.
Yeah, please.
Sir, while doing this word tokenization, will it differ from person to person? Means the length of the tokens.
It won't be.
So I was getting 118, sir. I guess you got 126, right? But for the same text data, I'm getting only 180.
118.
118. Yeah, sir.
Is it the same paragraph?
Yeah,
Can
sir, the
you
one.
please display the paragraph and see? Because I may have a couple of sample.txt files. I am doubtful whether this is the paragraph you are also using.
Yeah, sir, this is the one. Computer vision, yeah.
What is the last line? Highlights and color temperature.
Exactly, sir.
Is it showing the number of sentences? Six sentences are there. You do sentence tokenization and check the number of sentences. Because I'm having some 2-3 sample.txt.
Yeah, sir, it is showing 6 only. But words, it's showing 118.
Yeah, same for me also.
Is it on Jupyter? Sir, whether they're trying on Jupyter or Colab, it differ, right?
Maybe the versions also matters. See, I'm not sure about some updated versions. It's we have to verify that you just display your words and see that. For me, see, dot and comma also named as a separate token. Maybe probably it is not bringing dot and comma for it. That makes the differences. You just display all the tokens and see whether you have got this dot and comma punctuation marks as a separate token. See, I have got dot, punctuations, comma as a separate token. If that is not there, probably your version is filtering out that dot and commas.
Yes, sir, even I'm getting dots and commas. It might be because of Jupyter and Colab, I guess. It might be.
It's because of this apostrophe with words, I believe. Like it's so here for you, sir, it is showing it as one word and is as a second token. But for me, it is showing as like one token, like slightly different.
Okay,
Like,
this it's
yeah, like this. So this is like 3 tokens. For me, it is just showing as one token. So I guess just
yeah, that may be the difference. So the version, your package version variation, how it treats this.
Yes.
So don't worry, we'll be moving on to some advanced methodology there. Your advanced pre-processing method will take care of everything. You no need to do from the scratch this step by step.
Sure, sir.
Okay, so where we were, okay, frequency count. Okay, we are in the frequency. This is the most common, the top 10. You can see the token and how many times it is being appeared in the character. In fact, this is the approach is being followed as a one of the approach. Count vectorizer. Of course, this is the first approach after the very crude approach people have followed, which is the dictionary approach. Dictionary approach is also a very crude approach. Just for an image, I told you, right? For an image, how a 2D image is being converted to 1D, which is a very crude approach. People are, they generally, they don't do it. Either you manually extract feature or you apply CNN layer. That is the best approach. But however, we have done one exercise on the crude approach, right? Similarly, on the text also, early days, they have followed an approach called very preliminary stage. But immediately they migrated to count vectorizer. This is basically the count vectorizer approach. So before this count vectorizer approach, they were using a dictionary based. Assume that suppose you are going to build some NLP application on a specific domain. So maybe on social media data, okay, some Twitter feeds, or you're going to do some kind of a hotel review analysis or Amazon product review. So whatever the NLP application you're going to build, it is always specific to certain domain. Okay, we'll be narrowed down the domain, whether on the fashion products or electronic products to that specific domain you'll be working on. That means always you have a pool of or corpus. We used to say pool or a corpus of unique tokens pertaining to that domain. Say for an example, in Amazon, you just go to one category, electronics. Just go to electronics. Electronic, it comprises of laptop, mobile phone, earphone, iPad, so many things. Put together all these products. If I collect how each and every products have been described for all the electronic products, suppose I'm collecting a corpus of, okay, 30,000 unique tokens. 30,000 is too big, but okay, maybe I will say some 5,000 unique tokens. To describe all these, after cleaning all these stop words, we are not going to have these kind of words. We'll be filtering out English stop words. Okay, after cleaning all the English stop words, comma, full stop, punctuations, all those things, we got only the unique tokens alone, 5,000. Now these tokens are being arranged in alphabetical order in the dictionary approach, in alphabetical order. Okay, token number 1 to token number 5,000, like a dictionary. Like how in a dictionary, if we wanted to, for example, if you wanted to represent a word pixel in a dictionary approach, once you have arranged in the alphabetical order A to Z, okay, the word pixel, the location of the word pixel is at the location, say for example, it is 1426th location. Each and every token is being represented as a size of 1 cross 5000 one hot encoded representation. One hot encoded representation. Either 1 cross 5000 or 5000 cross 1. Doesn't matter, vertical or horizontal. The location number 1426 alone hot, okay, the remaining all are cold, zero representation. Then if I have another picture, another token called picture, actually picture will come before pixel, no? According to the alphabetical order. Maybe picture, the location number is 1386. 1386, the location is 1, the remaining are 0. This is the way they have used as a very crude approach, a dictionary approach. But immediately they drop this approach. This is not an effective approach. So from this approach, immediately they moved on to the count vectorizer approach. What do you mean by count vectorizer approach? These 5000 tokens have been arranged as 5000 columns like this. 5000 columns. Token number 1 to token number 5000. 5000. Suppose I have a product 1, product A, because it's electronic product, right? It's a laptop. Laptop, the description of the laptop is not going to accommodate all 5000 tokens, isn't it? Okay, the laptop is being how a product A, suppose a laptop is being described as the specification is being described. Okay, this is a very compact, elegant laptop with a thin bezel, a 14-inch display, and with the specification, all those things, lightweight laptop. Some description is there. Hardly it may utilize out of the 5000 tokens. Maybe it utilizes some 30 to 40 unique words. Okay, one of the token is laptop itself, right? Then definitely there is a laptop will come, screen will be there, keyboard will be another token will be there. So here there is no specific order. Please understand, here there is no specific order, no alphabetical order, nothing. Any order it can be. You just see that, okay, product A, how many times the word laptop has been occurred, just like this, the frequency count. Just to do the frequency count. For example, the product A, the laptop, the word laptop has been used 3 times. Screen came 2 times. Keyboard came 1 time. Another thing is the RAM. Okay, the RAM came 2 times. CPU token, it came 4 times. So they fill the entry with the word count. That is called count vectorizer. The another name for the count vectorizer is technical term to the NLP context, term frequency. Term frequency is nothing but that particular token frequency. For example, what is the term frequency of pixel? If I ask you, you have to say 3 for this paragraph. For this paragraph, what is the term frequency of pixel? It is 3. What is the term frequency for yes? It is 2. So that is, you can call it as a term frequency or the token frequency, the count of the token.
So one doubt here.
Yeah.
Sir, in earlier approach, we were building a matrix of, let's say if there are 5000 words, so then we are building a matrix of 5000 into 5000, right? But with this count vectorizer, there's only a single row, just 5000 columns.
Yeah, single row, 5000 columns.
Okay.
Exactly. Suppose assume that I have totally 100 products. What is the size of the matrix I will get after pre-processing? What is the size? 100 products. My size of the matrix is 100 cross 5000. Am I right? Each and every product is being described using 5000 tokens. So there are many tokens, their zeros will be there. Am I right? There are many tokens, 0. Because laptop is not going to consume all 5,000 tokens. Okay. A mobile phone has a different combination of the tokens it will consume. And the other location, it is a 0 count. The earphone will occupy different combination of the tokens. AirPods will occupy different combinations. So we get for 100 products, you will get 100 cross 5,000 matrix. What is the nature of this matrix? Any idea? What is the nature? Very good, sparse. Again, the sparsity is a limitation. In Python, it is you're going to say in the form of compressed sparse matrix, CSR matrix. People used to say in Python, it is a compressed matrix, sparse matrix as a CSR matrix. One of the bottleneck is it is very difficult to bring a sparse matrix to the TensorFlow framework. That is one bottleneck. That is one limitation. That is a reason. Okay, that is a reason. Okay. First, I'll tell you one more evolution happened. Then I will tell you the recent one is a word embedding. After this methodology, immediately they have moved from a count vectorizer to the next approach called TF IDF vectorization. See, if you are not doing a deep learning model building using a TensorFlow Keras, but you are using for some other application, say for example, I'm building a simple machine ML model. See, not necessarily once I pre-process the text at the end of the day, there is no hard and fast rule that I have to build a deep learning model. Please understand. Please understand. This is being applicable for this statement is being applicable for our earlier discussion on images and the time series also. Okay, you have got a time series data set. Okay, time series data set. What we have done using a CNN based deep learning model, what we did, we have done a classification. Of course, for forecasting, if you wanted to do forecasting, you may use instead of using a CNN based model, you'll be using a LSTM model. Okay, again, this is a deep learning based model. Don't come to the quick judgment. Whenever we are going to use a time series data set, either we have to build a CNN based deep learning, of course, the one dimensional CNN, and or LSTM as a forecasting. Beyond this, there were many other applications also there. Can you tell me what are all the other approaches? Maybe one approach is I'll do a manual feature engineering, followed by I can build a logistic regressor. I can build a decision tree. I can build a random forest. I can use a support vector machine. If at all, if you are interested to build any ML model with the manual feature engineering approach, I can do that. Or for forecasting approaches, if you wanted to use the same time series data set for forecasting, you can work with the traditional models like auto-regressive moving average model, ARMA model, ARIMA model. So just because since our course is going to talk about the deep learning, we are talking about that alone. So don't come to the judgment that, okay, hereafter we have to follow only this approach or this approach. Beyond this, I can do plenty of other things. Even if once I have the feature extracted for this, assume that I don't have a labels. Assume that each and every data, you don't have a labels. Okay. Of course, you can generate the labels, provided if all the classes are kept in 2 folders. Assume a doctor has given one single folder. It is a mix of, assume I have got 500 files, 500 CSV files, all are brain signal. Unfortunately, they are not labeled. Labeled in the sense what? Already we have last session, we have got alcohol in one folder, control in another folder. If the doctor has not grouped the record in separate folder, he has given in one single folder. Sorry, Mohan, this is what I never thought that our data could be useful for AI modeling. This is the way I kept my data. Something you do and because I cannot sit with this 500 samples one by one. I cannot open and see manually to interpret. And of course, I can do it, but it is a hell a lot of time it will take. I don't want to spend my precious time on this. So what could be the approach you can do for this? See here, the problem statement and the context is changing. As the problem statement is context is changing, your approach also should be different. Don't go like a horse saddle. If I teach one approach, don't look every problem with that approach. That is why I'm telling you to, during the weekend, coming weekend, you don't have a class, utilize that to work with some different data set, because a different data set will throw you a different approach, different context. It is giving you a different context. For that context, how do you prepare the data also? There will be a slight variation. At the end of the day, your model is going to be the same. Okay, your data preparation is going to be unique for one context to the another context. Once you master that, any kind of challenges you can handle. For that, you should have an exposure to variety of contexts. You should get exposed to. That is what we say experience. Basically, what experience? Once you work with the multiple clients, every client will come with a different context. You got a varieties of approaches in your mind. That is basically your experience. Okay, in this example, all 500 data is in one single folder. What is your approach? Maybe, okay, you do some manual feature engineering. Come on, guys.
Can we do clustering?
Obviously, you can do a clustering. Once you cluster is going to give the label, attach the labels. Job done. So the contexts are different. Okay, similarly for the images also. Okay, images also. Once you have a manual feature engineering, you can work with the traditional ML algorithms. Even you can do the clustering job also. So even in the text also, there are so many other applications. Apart from the deep learning based models, you can do a recommendation systems, does not require, of course, some modern day recommendation system. One approach is a deep learning based recommendation system. That is one approach. Beyond that, there are other approaches are there, which is not deep learning based. There are different approaches are there. So the term frequency inverse document to frequency approach has been introduced. TF IDF vectorization. Why I'm talking about all those things is, unless otherwise you are not restricted to build a CNN based deep learning model or LSTM model. If your goal is something else, still you can work with count vectorizer, still you can work with the TF IDF vectorizers. Whatever the sparsity is a limitation for your TensorFlow backend, the other stuff, but still there are many applications. Even in current in market, in the business process, people are using few application TF IDF based vectorization. Just because the word embeddings and word to vec is being adapted, not every company is adapted. Still, there are many companies, they are happy with word count vectorizer and TF IDF. They may not be using CNN based deep learning or LSTM. Maybe some other applications they will be building. A simple recommendation system or even a clustering, some kind of application like that. So here you can see some additional term is being introduced called inverse document frequency. Now let us understand what is meant by this inverse document frequency. I told you, right? This is also same like token number 1 to token number 5000. Okay, you have a product 1 to product 100. As discussed, each and every product is being represented as a count. Okay, as a term frequency. Here also you have a term frequency. Term frequency will be there. Additionally, it is being scaled by some extra term called IDF. What is the purpose of the scaling? People thought that I no need to give weighting factor, so I don't want to treat all the tokens equal. Whereas in your count vectorizer, all the tokens are treated equal. Whereas in TF IDF vectorization, you are going to give some weighting factor for certain tokens. That weighting factor is called inverse document frequency. Say, for example, in all 100, okay, in all 100, suppose a particular a term is being appearing in all 100. Of course, after filtering all the English stop words and all, you have filtered. After filtering the English stop words, you noticed, okay, all 100 products, maybe that my TF score may be different, but in a particular token number, say for example, a token number 450, a token number 450, almost all 100 products, some count is there. For first products 3 times, 2 times, 1 time, 5 times, 2 times, 1 time. Can you give an opinion about this token? What is your opinion about this token number 450? Almost in all 100 product description, that particular token is appearing. Maybe the count is different. That is not a botheration. One product description only 1 time it comes. Another product description 2 times the token is coming. Some other product 4 times. Some other product 2 times. Some other product 1 time. What is your opinion about that token?
It might not be an important word or something that differentiates these 100 products.
Very good, very good. So if a particular token is being appeared in almost all the 100 products, that means that token is not differentiating my product from others, isn't it? So what is the formula for this inverse document frequency? The logic is very simple. Log base 2, I have 100 products. I have to see each and every token. We are calculating this IDF is a weighting factor for each and every token, right? Log base 2. If this token is being appeared in all the product description, all 100 divided by the total product, it gives me log 1. Log 1 is 0. That means the weighting factor for token number 450 is simply 0. After all, the token is being appeared in all 100 products. Why should I give an importance to that token? On the other hand, say for example, my token number 568. A token number 568, only 10 product, they have a description about that token 568. Only 10 products. Remaining 90 product, they never come across that token. So the weighting factor for token number 568 will be very high. The reason is log base to 10 divided by 100. Because the token number 568 is being appeared only in the 10 product. Of course, this weighting factor is more, right? Compared to this weighting factors. For example, 90 product out of 100. Whose weighting product will be more? Obviously, this weightage will be more weightage. Comparatively, this is a less weightage. Because out of 100 product, 90 products, this token is being appeared. Out of 100, only 10 products, this token is being appeared. So this token will have a higher weightage compared to this token will have a lower weightage. You understood the meaning of IDF? Each token will be giving a weighting factor in the TF IDF vectorization. Whereas in the count vectorizer is simply only the term frequency. There is no weighting factor. With weighting factor is called TF IDF vectorization. Any question, guys? You are with me?
Yes, sir.
Yes, sir.
So the most recent one, let me reserve that the latest development. Towards the end, I'll give an idea. Tomorrow only we are going to discuss about that. Of course, the implementation also tomorrow. Based on the count vectorizer and TF IDF vectorizer, couple of processing we are going to do with some real data set. So before that, I'll demonstrate a few more examples that I will do with this basic samples. I will show you the English stopword filtering. Okay, let us see how to do the English stopwords filtering. For that, you download NLTK download stopwords. It will take all standard English stopwords. What are all the English stopwords? So from nltk.corpus, import stop words. You can import this. You can set the stop word as English. Some standard languages it's being defined in NLTK. Suppose if you are working on the foreign languages also, it will support German, French and all. So we are working out model for the English words. So I set my stop words English. So W for W in words updated, if not W in stop words. So words filter other than English stop words, if not in W is in English stop words. So it's a complement of it. So only other than English stop words, your filtered words will be available. So the filtered words I'm storing in words filtered. I'm displaying the top 30. First 30. Now you see the first 30 alone I just displayed. Computer vision, way, convert, pictures, pixel, make, sense, picture, pixels, the ability, machine, take, step. There is no English stop words. So what is the length of the words? If you see, after cleaning all the English stop words, okay, we have got only 50 tokens. 50 tokens are there, which is not an English stop words. So now I do the frequency distribution. Okay, now I do the word count for the words filtered. Now you are going to have a meaningful content about this word description. Earlier, you can see the top 10. Okay, top 10, it was including the English stop words was showing. Okay, now it is going to take the content. This is actually the content. Okay, this is a content about some technology content, right? This is about some technology content about computer vision. You can see the word pixel used 3 times, pictures 3, color, computer vision. So this is a content about some computer vision and image processing related stuff. We can easily understand about the nature of this text. So if you wanted to visualize the stop words alone, you can print the stop words and you can see. Stop words alone, if you wanted to see, you can see all the stop words are being collected. All stop words are here. All stop words are collected. Sometimes again, according to the context, sometimes what people they fine tune the tokens based on the length. Okay, it is just some context it will be useful. Some context, if they feel that the tokens are too exhaustive tokens, I wanted to limit the size for the computational to reduce the computational time and all. Only for that context they'll use it. But just you understand that. Suppose I do fine-grained selection of words. I wanted to filter. Okay, only I wanted to keep the tokens at least more than 3 character. Greater than 3 alone I wanted to. Less than 3 character I don't want to keep. That kind of a token. If you wanted to do that fine-grained selection of words. So now after cleaning the English stop words, my token size reduced to 50. Okay, now I do the fine-grained selection of the words by specifying the length of the tokens. Length of the tokens greater than 3. Now you can see further I'm reducing my token size from 50 to 40, 50 to 46. That means there were 4 tokens. The length is not greater than 3. So it is below 3. So this is updated. So NLTK package supports Indian languages, many Indian languages. If at all, if you are interested to explore that, you can see corpus of, it is having a corpus of Hindi words. So you can see some standard Hindi words corpus has. Some many foreign language words also supporting. So the respective thing you have to download it. I would like to show you this TF IDF vectorization, how to perform this TF IDF vectorization works. So you can import this TF IDF vectorization. from sklearn.feature extraction package. So keep this library ready. Okay, now we have worked on the sample small toy data. If at all, if you wanted to work on some real text, I told you copyright free texts are available in NLTK. So first I'm downloading those books. So each and every resources, very exhaustive resources are available. A web text alone is being available in separate corpus. All the novels alone, popular story books are available in this Gutenberg. So category wise, it has a very rich resources. So I have downloaded all these packages. Latest approach is a word embedding, word to vec. Okay, word to vec. So I download these. So totally there are 9 books. You can see Wall Street Journal. If you wanted to read this, text 7. Okay, let us read this Wall Street Journal. Some pre-processing if you want to do with this Wall Street Journal. Let us see how many tokens are there. Unique tokens are there in the Wall Street Journal magazine. You can manually, you can remove this also. See, I told you, right? See, some version does not support this punctuation removal. Certain functions default, your Python function supports that punctuation removal. If you wanted to do that explicitly, if you wanted to do that, you can do this transformation like this. String dot make trans, the string punctuations. And if you do the translation for whichever your source data, if you apply, your those things will be stripped off. So text 7 I have taken. You, whichever the text you are interested in that, you can take it. This is one of the popular television series, and it is later on it has a book also. Have you heard about? There is a story behind this, you know. You know the founder. Who is the Python founder? You can Google it and you can tell. So when he was formulating the software, he wanted to announce to the world. Okay, he wanted to name the software some unique name. Should be very catchy, very unique. So before he was addressing that software to the public, the world community, why he got the name the Python strike in his mind is his kid was watching this popular series at the time when he was developing that software. His kid was watching the series Monty Python and the Holy Grail, and he found that it looks very catchy. There was a backstory behind that, how he named the software as a Python. This was the inspiration for the naming. So that book also available here. Okay, now let us see for the text 7. I have Wall Street Journal I have loaded. So I do this filtering, punctuation, comma, all those things cleaning, followed by lowercase filtering I do. You can see the total length of that content is, okay. Still, we have not removed the English stop words and the alpha, non-alphabetic things and all. Now it is a 10, so 10 lakhs, sorry, 1, 2, 3, 4, 5, 1 lakh 6,000, sorry, 676 tokens are there. Okay, Afterwards, I'm going to remove other than non-alphabetic tokens. I'm going to remove, and I wanted to check what is the updated token in this content. So from 1 lakh, it is reduced to 80,000, 80,046. Okay. And then I'm going to remove all English stop words. Remove all English stop words. All English stop words. Now let me check the updated length. From 80,000 tokens, almost reduced to half, 48,561. See, remember this 48,561 tokens, including the same token as repeated many times, chances are there. But if you wanted to see the unique tokens, you can see set, and you can see the what are the out of this 48,561 tokens, what are all the unique tokens. You can use set function to the overall tokens and get the length now. Now these are all the unique tokens. Unique tokens were 9,732. 9,732. Now, whatever the process you have to do it manually step by step, everything is embedded in one single package, this TF IDF vectorizer. Whether you do TF IDF vectorizer or simple count vectorizer or the advanced word embedding, okay, all the pre-processing will be taken care of. Everything will be taken care. You don't need to do all these things manually. Finally, it is going to work out the final numerical representation for your unique tokens. Unique tokens. Now let me demonstrate how to use TF IDF vectorizer for some real data. Okay, this is I have used this built-in data set which is being available in the NLTK package itself. Okay, now I'm going to give you some once again a data set which is not a copyrighted one, but it is a real data set. Okay, it is being shared with public. Some 500 products, some fashion products are being described. So download this. The name of the file is called Fashion Store. So we are not going to build any application over this data set. Just I wanted to show you how your TF IDF vectorizer is going to tokenize your input data set and how it tricks. Maybe I just give some a simple idea. Once we got this TF IDF vectorizer, what are the things we can do? Okay, import this library. First, let me read this. It's a CSV file. So once you have read this and see the head of your data set, some 500 products, fashion products are there. So head and tail, you can see ds.tail, last 5 products and first 5 products. I have just 2 columns. Product ID. So product ID number starts from first product to the fifth product, and it goes up to 500 products. So we have 500 products, right? The Python index starts from 0 to 499. Cargo shirts, cap to bottoms. So any one product alone, if you wanted to see the description. So description column alone, if you wanted to see, for example, let me see all wear cargo shorts. Okay, all wear cargo shorts. It is a 498, right? Okay, so all wear cargo shorts is index, Python index is 498. You can see the description of this all wear cargo shorts. So this is, so randomly you can check any cap to crew 496. See the description. Bass player, many products, including some surfing products are there, mountaineering products are there, mountaineering high altitude jackets. So many ladies wear, so many things are there in this. Okay, we have 500 products. So now let us see how to initialize your TF IDF vectorizer to tokenize this. Okay, not so earlier we have seen just one particular sample, right? Which is a Wall Street Journal. Now, if you have a pool of records like this, here I have totally 500 products. So we are going to have something matrix called 500 cross some unique tokens we are going to get. 500 cross unique token, put together all 500 products. After filtering out all the English top words, how many unique words are there? And we are going to have a TF IDF matrix we are going to get. So 500 cross unique tokens. Unique tokens put together 500. Just now we have seen the unique tokens for just for the Wall Street. We got some 9,000 something. Similarly for product 1 to product 500. Each product is something a different varieties of products. As I told you, the surfing products are there, mountaineering products are there, high altitude products are there, hiking products are there, beach wear, ladies wear, children's wear. So many products are there. So put together all the products, how many unique tokens are there after filtering out all the English top words and all. Your TF IDF vectorizer is going to give that unique tokens. So here, this is how I'm using this TF IDF vectorizer. I'm calling the function. Let us see what is the meaning of each and every argument. You can use this TF IDF vectorizer for both word tokenization as well as sentence tokenization. Only thing you have to say that whether this you wanted to use this analyzer as a word tokenizer or a sentence tokenizer. Here I have specified, here I wanted to construct for word tokenization. That's why I'm saying that's word. If you wanted to use the same thing for sentence tokenization, you can use it as a sentence tokenization. And the second variable is n-gram range. N-gram range. So here I have specified in the form of a tuple 1, 3. You know that 3 is not inclusive. That means 1 and 2. So this tokenization will consider unigram and bigram. What do you mean by that? You know what is bigram in English words. For example, when I write t-shirt, t-shirt will be taken as a bigram. Will be considered as. So you have to tell that whatever the bigrams are there, include bigrams also. T-shirt should be considered as a separate token. So maximum we need a unigram and bigram tokens. So that is the meaning of the n-gram range. So 1 and 2, I need a unigram and bigram tokens. And stop words. This is, you don't need to, I told you, right? Stop words English, all the your comma punctuations, apostrophe, and all the English stop words will be removed. On top of that, you have a control mechanisms to control your unique tokens. See, already TF IDF, your inverse document frequency is going to give the weighting factor for the tokens. Beyond that, if you wanted to control the size of the matrix, if you feel that, okay, I wanted to reduce the size of the tokens, you can use this variable called min df. Here I have not used any cutoff. If you use this cutoff, drastically you can reduce the token size. Can you see the token size for me? I don't use any cutoff. My token sizes, unique tokens are 52,262 unique tokens we have got. Put together all 500 products. 52,262. So what is this min DF is going to tell? See, I have given one example. Say when I say 1%. So when I say min DF equal to 1% in terms of 0.01, I have specified. Ignore the terms that appear in less than 1% of the document. Less than 1% of the document. I don't want to consider those tokens. You can set that percentage. Ignore the terms which is appearing less than 2% of the document, less than 3% of the documents. So I don't want to have any control mechanisms. If at all, if you wanted to have such control, you can use this min DF score. You can set some percentage. Okay, 5% if you wanted to set that, you have to pass 0.05. Now, without any such cutoff, when I run this, okay, so I have to pass only to the description. Only the text portion is available in the DS description.
Excuse me, sir.
Yes,
Sir,
sir.
I didn't understand bigram. Unigram would be like one word, and bigram would be like
Vice president is a bigram. T-shirt is a bigram. So in English, which are all the bigrams words are popular bigrams? Two words connection. T-shirt, vice president. There are so many bigrams are there. No, you are telling the model to keep the bigram as a separate. I don't want to keep vice separate token, president separate token. Vice president should be kept as one token. T-shirt should be kept as one token. That is a bigram words.
okay.
I'm not sure about trigrams. I don't see any English words. There is no trigrams. So 1 and 2 maximum unigram and bigram words the tokenization will do. See, now I'll give some threshold for this. Now I'll show you. You can see the reduction in the token size. 0 point. I wanted to set 5%, 0.05. Massive reduction. Can you see from 50,000 reduced to 539? But you will miss the details. Okay, let me try 1%. 1% alone if I eliminate. It's 4,657. If you see, you can again, only after experimentation, only we can come to know that whether it's the right representation, good to go for the application. And if you see that your application is not doing a good job, so don't set any cutoff. Better you work with the full corpus. Anyhow, IDF is going to give the weighting factor, right? So we separately, we don't want to control this. So let me work with the full matrix. So 52,262. Okay. So once we have successfully prepared your text to the numerical presentation, now once you got the numerical representation, whatever you wanted to do, you can do any application. You can do, if you want, if you can do the clustering, you can do clustering. I can build a recommendation system. I can build a traditional ML algorithm. Traditionally, any ML algorithm I can do. So only complication is I cannot do a TensorFlow based any development because the sparse matrix representation, your TensorFlow will not support this representation. So this sparse matrix you have to convert to tensor sparse tens layers, and it's a bit complicated. So only there are certain representation your TensorFlow will support. But other than your TensorFlow based framework, you can do many application you can build based on this. One simple application I'll just show you. Imagine that you wanted to do a content based recommendation system. Okay, I wanted to build a content based recommendation system. Now you have this TF IDF representation. $500 products. First product to 500 product. You have got 52,000 tokens. Okay. Suppose I wanted to see if suppose as a customer is seeing the description of this product one, Okay. Same thing happen in Amazon also, right? Suppose whenever you see a product description, you see the product description. And in the bottom, you can see the top 5 products similar to this product, whatever you are viewing, similar products. How basically this works? It's a very simple content-based recommendation system. After all, your product 1 is being described as the frequency of occurrence of which tokens. This product is being defined as the frequency of occurrence of which token. Of course, it's the token is being weighted. If at all I wanted to know the product 1 is similar to this is the top 5 similar product, what they could have done it internally. The simple logic. What they could have done internally. Okay, for simplicity, let me take a small matrix. Product 1, product 2, product 3, product 4, product 5. I have 5 tokens just for simplicity. T2, T3, T4, T5. After your term frequency multiplied with IDF term, this is my first product description. Second product description is like this. Third product description is like this. Fourth product description is like this. Fifth product description is like this. If I ask you which 2 products are similar, you can easily tell. Which 2 products are similar products?
First, third.
Yeah, obviously. Because the first and the third products are being described using token number 3 and token number 4. But slightly this score is different. So you visually you see and you are observing this and you are telling, but how computer will understand? How computer will understand first and third are similar? To make the computer to understand, what should I do?
On the basis of sparsity.
Huh?
On the basis of sparsity. Like
Sorry?
on the basis of sparsity, maybe we can.
Sparsity.
I mean the columns for which it's empty.
On the basis of weight, sir. Comparison of weights.
We are complicating the things. No.
Yeah, it's simple only. We extract the features with non-zeros and compare against the other.
We are complicating the things. See, it's a very simple solution. You are telling all hi-fi jargons. See, basically computer has to understand, okay, first product and third product are closer. First product and second product are not closer. Just simply it computes the distance, guys. Distance. See, 0 minus 0 the whole square. If I compute Euclidean distance, 0 minus 0 the whole square plus 0.23 minus 0.35 the whole square plus 0.35 minus 0.42 whole square plus 0 minus 0 whole square. I just simply calculate Euclidean distance or Manhattan distance or cosine distance. My job done. You calculate the distance between 1 and 3 and 1 and 2, whose distances are, see, if you see 1 and 3, you calculate the distance. At the same time, you calculate the distance between 2 and 4. Product 1 and product 3 distance is very small. Similarly, product 2 and product 4 distance is very small. Relatively, product 2 and product 1 distance will be farther, isn't it? If you calculate distance between 1 and 2, 0 minus 0.35 whole square, 0 minus 0.2 whole square, 0.23 minus 0 whole square, you will get a high value. My distance will be large.
And how will system or algorithm basically know what is high distance and low distance on relative terms?
Whichever is see, if I wanted to recommend a top 3 product to this, no, each product 1 is just compute distance to record 2, distance to record 3, distance to 5. How k and neighbor works? K nearest neighbor, how it works?
It
Any
checks with
test,
all data points.
any test record you present and your k neighbors, you say n neighbor, 5 neighbors, you say that if it is a classification model, first of all, it has to calculate distance to all the records and pick the closest to 5 records.
Right.
And closest to 5 record, it check the, if it is a classification model, label it, check who is the majority, it declares. If it is a regressor, check the y value, take the average. Here is the recommendation. Just simply, if I wanted to recommend top 3 products for the first record, simply calculate the distance to the remaining 499 products. Product 1 to product 2, product 1 to product 3, product 1 to product 4, product 1 to 499. Possible? Can I sort all these guys from the closest to the farthest, smallest to the largest, recommend top 3 or top 5 you want. That's all, as simple it is. Let us not complicate the things. Simple and straightforward. Are you getting it?
Yes, sir.
So see, there are so many distance metrics are there, whether I can use Euclidean distance or Manhattan distance or cosine distance. Here for the illustration purpose, I have taken cosine distance. Of course, the cosine, you know, if you are familiar with the cosine distance is based on cosine similarity formula. Okay, if you are not aware of cosine similarity formula, just I am telling you, cosine similarity formula is nothing but, for example, this first record and third record, I need to, like Euclidean distance, I need to compute the cosine similarity score. I need to take a dot product of first record and second record, dot product divided by norm of first record into norm of second record. So how to compute this formula? Dot product means 0 into 0 plus 0 into 0 plus 0.23 into 0.35 plus 0.35 into 0.42 plus 0 into 0. That is numerator. Okay. What is the denominator? Norm of vector 1. Okay. Root of 0 square plus 0 square plus 0.23 square plus 0.35 square. That is this into root of 0 square plus 0 square, 0.35 square plus 0.24 square plus 0 square. This is give you the similarity score. See, similarity score is the opposite to distance. So whenever I compute the similarity score for 1 and 3, my similarity score is very high. Compared to similarity score for 1 and 2, my similarity score will be lower, right? Lower the similarity, larger the distance. Higher the similarity, smaller the distance. So my cosine distance is equal to 1 minus cosine similarity. If you wanted to operate everything as a cosine similarity, very well and good. Okay, instead of arranging smallest to largest, imagine if I compute cosine similarity score. Okay, instead of distances, I'm calculating cosine similarity. How should I sort this? Largest value to smallest, isn't it? Highest similarity to the least similarity. Or in terms of distance, if you arrange smallest to largest. Your distance and similarity scores are complementary to each other. Please understand. So here I'm applying, actually this kernel function is using the formula, cosine similarity score formula. A dot B divided by norm of A into norm of B formula. It is using that. So for that, I have to use the function linear kernel. The syntax is to get that matrix 500 cross 500 matrix. Basically, we are going to get a 500 cross 500 matrix, isn't it? Actually, it is going to give you the cosine similarity score like this. Product 1 to product 500, product 1 to product 500. How first product similar to first product? 100%. The similarity score is 100%, like your correlation score. So my diagonal is basically 1, isn't it? So it is going to give a symmetrical value. So your lower diagonal will be symmetrical to the upper diagonal. That means product 1 similarity score with the product 2. You can see the score. The same score is 1 versus 2. The score are symmetric. So for that, I have to pass my TF IDF matrix 2 times. I have to pass it. So the linear kernel will do the computation. It will take the first product from the first matrix, second, same first product. So I'm just giving a duplicate of the same matrix. Basically, I'm just giving a duplicate of the same matrix, 52,000. 500 cross 52,000. What it will do? it will take this first record, it will take the first record, do a dot product. Of course, the score will be 1. Self-similarity. First record with the second product of this, it will put the record here. First record with the third record. First record with the fourth record. Likewise, it will keep filling. Then second record with first, second record with 2. So it will going to get a 500 cross 500 matrix. That matrix is called, I'm going to name it as a cosine similarity matrix. Let me run this matrix and I'll show you how this value looks. Let me display the first row alone. Let me display and I'll show you. You can also run this. This is, I'm just displaying the first row of your 500 cross 500 matrix. You can see the shape is 500 cross 500. How to interpret the first row of 500 cross 500 matrix? What is the interpretation? What is this one? Product 1, 100% similar to the product 1. The self-similarity score. What is the similarity score from the first product to the second product? This is the score. First product to the third product. What is the score? Actually, the size is, it is 1 cross 500, right? Row vector. Just because we don't have a space here to display the one lengthy vector, it is being displayed like this. Don't think this is a matrix. Actually, it is just a one row vector, first row of your 500 cross 500. Now, if I wanted to know which is the top 3 product, closest to 3 product for the first product, what can I do? Simply can I short these guys? Can I short this? If I short this highest to the least, okay, I'm going to do the arc short of this. You know what arc short will do? Arc short will, by default, arc short will do in ascending order, like smallest to the farthest. Okay, make a comment if you want. By default, okay, smallest to largest. But it is not a distance. If it is a distance score, it is okay. But this is a similarity score. For similarity score, largest to the smallest arrangement, right? So better you can take the bottom, from the bottom, you can pick the top 3 or top 5. You can see what is the meaning of the 0th index. Actually, it's arc sort. We are doing arc sort. Arc sort is going to arrange the scores based on the similarity scores, but it's going to return the index, Python index, 0 to 499, right? 500 products, your Python index is 0 to 499. So when I do arc sort, okay, in the arc sort, I'm taking the last 5 indexes because it is the smallest to the largest. So the 0th index is nothing but my self-similar score, product 1 similar to the product 1, 100% similar. That is why 0th index. So leave this guy. So the top 3 recommendation may be Python index 18, Python index 493, Python index 17. These 3 are the top 3 recommendation for the first product. Okay, if you are very curious about to know about DS of description, index number 0, it is active classic boxer, right? That is the active classic boxer, similar to the same active classic boxer, 100%, because that is the highest value, right? Similarity score 1, right? 1 is the highest similarity score. So this is being arranged from the smallest to the largest. So your 1 is being arranged in the last. But here you are not seeing the cosine similarity score. Rather, you are seeing the Python index. So active classic boxer, 100% similar to the active classic boxer. That index is 0. Okay. So let us leave this guy. Let me check who is the first closest to the active classic boxer. That is the 18th index. Cap 1 boxer brief. Second closest is 493, index number 493. Again, another active boxer brief. Then index number 17. Which product is in index number 17? Cap 1 bottoms. Suppose if you wanted to check top 5 recommendations or top 3 recommendations for product number 1. Let us check what is product number 1. Active sport boxer brief, maybe something else. Let me check. Okay, baby sunshaded top. Now I need to see the top 3 recommendation for the similar product, baby sunshade top. What can I do here? In the place of cosine similarity, $10. Okay, product number 10. These are the top recommendations. Okay, here you go and change your. Now you wanted to see the top recommendation for the product number 10. After org short, you see the last 5. The product number 10 similar, 100% similar to that product itself. Product 10 similar to that product itself. Okay, that is why you got 10. Leaving the 10, let me check the remaining index 419. Sorry, 418. Let me check who is 418. The customer is now seeing the description of baby sunshade top. Now in the bottom, you wanted to see the top 5 recommendation. 418. 418. Baby sunshade top. Sunshade hoodie. Okay. Next is 464. 464. This is the product. 347. 347. All are related to the baby product. You can see this. Run shade t-shirt. These are the top 3 recommendations. Same way, whichever the product you wanted to give a recommendation, the respective 100th product. Let us see what is the 100th product. 100th product is some shirt. Okay. If you wanted to see the top 3 recommendation for the shirt, 100 similar to 100 itself. So let me check 122. Some patola shirt. Special edition patola shirt. 217. Sleeveless shirt. 224. All are related to shirt. Okay. So your similarity scores work well. This is one simple application. See, once you convert your text to a numerical format, anything you can do. But here to our context, we have to build some models, right? Deep learning based models. Up to this, do you have any question, guys? The same kind of a data preparation I have done for multi-class. Of course, this is 500 products. Here I wanted to demonstrate TF IDF vectorizer. One more data pre-processing I have done with a different set of data set. That is a simple count vectorizer. Count vectorizer. Using a simple count vectorizer, I can build another application like a recommendation system. You can do another application. So once we see how count vectorizer and what kind of application we are building, finally I'll take you to the most advanced, the recent representation, which is called as a word to vec or word embedding. So only to grasp the basic, it will take time. Once you understand the basic idea of this representation, whatever the application, building the application, once again, the same model, your model building part will be the same. Validating the model, that will be the same. So that part is going to be nothing new for you. Only these portions are new to you, the data preparation and these pre-processing steps. Okay, let me introduce the other 2 data preparation. Word count, simple count vectorizer followed by word embedding. Word embedding. Word embedding is actually a part of tomorrow's content. It's a part of session 8. And the count vectorizer is almost same like your TF IDF vectorizer. Only thing, you don't have this IDF scale factor won't be there. You don't have a weighting factor for it. A simple, it will have a term frequency alone. Okay, term frequency. Only the package I have used is different. Tomorrow I'll demonstrate this. I don't want to hurry up now. So only this portion, the way in which I'm representing the data preparation part, this alone is different. Instead of using TF IDF vectorization, I'm using a TF IDF transformer and count vectorizer. So my package utilization is different. So this portion is different. But once again, I'll get a matrix representation. So once you bring your data in a matrix representation, I have demonstrated one modeling. Of course, the limitation I told you, these kind of a count vectorizer or TF IDF vectorizer or basically a sparse matrix, these kind of sparse matrix, your TensorFlow framework will not support. But other than your TensorFlow framework, you can do other application. Like using a TF IDF results, we have used one simple recommendation system, right? Like a count vectorizer, once you have a count vectorizer setup, okay, I have built a neural network model, but not using a TensorFlow framework, using a simple sklearn framework. sklearn framework, I have built a NN model. Actually, here it is a news article. There are 4 different news articles I have taken. One is a sports article, baseball and science and medicine, and Christianity, religion article, and politics article. And I wanted to see, I displayed one article, how it looks. See, this is a science and technology, electronic science and technology. This comes under science and medicine. Okay, you can see this is an article. So all the articles are came in like some email format. Actually, this is how the data set is. Now the model has to successfully tell that which article belongs to which category based on the content. Whether it is a political article or a sports article or science and medicine article, I have constructed a neural network based NLP classifier model, and I have reported my classification report. Now you can see each and every category is being almost with a very good level of accuracy is being retrieved. Almost 4 article successfully model classified successfully a neural network model. Only difference is I have not used the TensorFlow framework. The limitation I already told you. Even any live record, if you present, say for example, I have 2 records, some production data. Say I say God is love. I think that ketosis can occur in lesser degree. Some scientific terminology. I'm just passing some random. Assume that some production word. I have to prepare my data set. I should go through the same process. Okay, your count vectorizer followed by your transformation, and the trained model you can call to predict your production data. For example, when my production data says that God is love, the model says that God is love comes under religion article. And this is a science and medicine, right? This should say that my model should say that it's a science and medicine. So this application, let me demonstrate tomorrow. We'll go through in detail tomorrow. I'm just quickly just navigating. So what we have done is why we didn't do a TensorFlow based framework here. I have demonstrated with sklearn based neural network based model. We have solved a multi-class classification. We are classifying 4 different texts by using another type of transformation approaches by using a word count vectorizer approach. So once you finish this discussion tomorrow, I'll take you to the most recent approach, word embedding approach. So first we'll understand the word embedding, word to vec approach as a standalone approach. Pre-processing alone we'll discuss with one exercise. Once we appreciate the concept of word to vec, then I'll take you one more real data set. We'll take and we'll build a full-fledged DL architecture using a TensorFlow and Keras based DL architecture. For that, I have taken an application as a sentiment analysis. We are having some positive reviews and negative reviews. Again, it's for the real data set. Again, it is a copyright-free data set. I'm going to use it. It has a corpus of some thousands of positive reviews and many thousands of negative reviews. Documents are there. We are going to pre-process the data set based on the word embedding concept, most advanced concept which is being used followed nowadays. And we are going to successfully classify those positive and negative reviews based on the CNN based TensorFlow framework. We are going to work out, build the model. Not necessarily whether CNN layer is needed or not. Tomorrow we'll discuss to the context. So basically, we'll be using tomorrow we'll be using a TensorFlow framework and Keras framework to build the deep learning architecture. For that, the processing itself, it is a unique processing, which is a word-to-vec word embedding processing. Okay, so that is the agenda for tomorrow's session. Tomorrow we have a session. Okay, because since weekend we don't have a session. That is why 2 consecutive days this week we have a session. So after tomorrow's session, your next session will be on the Monday evening. So I want that each one of you try to build a CNN based model for some different unique image data set, and similarly one-dimensional CNN based model for a unique data set on the time series data set during the weekend, and come up with your results, and you can ask me any questions related to some different context. That is the way you can expand your horizon in approaching a different variety of problem. So your core algorithm remains same. Your data preparation part will vary from one problem statement to another problem statement. At least try to get a new exposure with another kind of a problem statement, another kind of a data preparation part, some unique data preparation part you try to explore with a new data set. Please use a copyright free data set, because I am not liable. If you are bringing your company data set, I am not responsible to expose your company data set in this forum. That is claiming I'm telling you. Please, if at all any data set you are going to bring in this forum, make sure that it is not an intellectual property data. You're not supposed to share your company data with me. Okay, so make sure that come with any copyright free data. You take it from the many resources are available in the internet. You work out during the weekend. Come up and tell me the challenges you have faced and how do you build them on, and share your experiences. Maybe first 15 minutes we'll discuss your results, and then we'll jump into Monday. Actually, I'm going to introduce a new interesting neural network architecture, which is a recurrent neural network. Based on the recurrent neural network, we are going to build the interesting applications using LSTM models. That is the agenda for the next week discussion. And finally, the last week is another new model, which is a reinforcement model. Practically, they are very less used model, but however, that is the future. People are trying to, still they are mostly in the R&D part. Not commercially, it is very less. Hardly I can say only 10% is application. But it will take some time to get matured, or that field getting matured, but you should be get exposed to that area also. So your last week is going to talk about the reinforcement learning, and the next week we are going to talk about RNN based, recurrent neural network based model. Okay, with that I am going to close today's session, guys. If you have any quick questions, you can ask me today.
Sir, yeah. In the beginning of this model, we have imported this PU Enkite, right? Something. What does it do, sir?
That is a part of your NLTK tool. Some of the packages are available. It's available in the PU Enkite packages.
Okay.
It is supporting after importing NLTK. You have to do that. See, inside NLTK, there are so many sub modules are there, sub packages are there. If you wanted to utilize all those sub packages, each and every sub packages of NLTK, you have to download those sub packages also. So just by importing NLTK, you are not immediately, all the sub packages are not readily available to you. So to make use of those sub packages, we are importing that.
Okay. Thank you.
Anyone is currently working on NLP projects? Out of you, for Eric, Mohan, Shahil, Rashid.
I have worked on one of the small data sets, sir, for my company itself, for an organization. It's like sentiment analysis only. I have used text blob and Wadir sentiment. Based on the polarity scores, I have decided like the sentiment of it. Simple.
Yeah. And how do you do the pre-processing? How do you prepare the data? What kind of pre-processing you have done?
That is what, sir, by using regex and all,
Okay.
Yeah. Cleaning method, removing the stop words, punctuations.
No, see, that is a standalone approaches. Even without having a support of some external packages, you can use. I'm asking you the process. Finally, see that regex, stop word filtering, cleaning approaches. These are all the approaches just to bring unique tokens. Once you
Yes.
brought the unique tokens, how do you represent your text? Whether you are going to represent the text by word count, or you're going to represent the text by word count multiplied with IDF factor, or you're going to represent your token with word embedding. That is a representation.
We have used word embedding on this.
Yeah. So totally there are 4 representation. Once again, I quickly summarize and I close today's session. Number 1, dictionary. Nobody is using dictionary. One hot encoded. It's completely outdated. Nobody using. Second one is a simple term frequency count. That is a word count. Still people are using for few applications. Number 3, more improvised approach of word count is multiplied by IDF, TF IDF. That's what now we have seen. The more advanced one, the more robust one, even the TensorFlow framework will accept is the word embedding approach. Okay. So 3 approaches I have mentioned today's session, and the last approach here, that is a word embedding approach. Sometimes people call that as a word to vec. So word to vec is the word basic. See, the basic idea of that approach is called as a word embedding. Different packages, they name it in very fancy name. For example, a Gensim product is word to vec. Word to vec is the Gensim product. So they name it like a word to vec as a fancy name. So other than Gensim, there are many packages supporting this thing, but the names are different. But fundamentally, the idea is same. The mathematics and the idea, the background is same. Okay, your package name changes from one service provider to another service provider. So whatever you're going to use it as a Gensim package, that is a word to vec. Basically, it is doing the same embedding process, word embedding process. Any question, guys? Shall we close for today?
Yes, sir.
Okay.
Yes.
I will meet you tomorrow, 7 o'clock.